In section 2.5, we look at linear functions and models and also variation. So a linear function is a function of the form f of x equals mx plus b, where m and b are constants. So remember that this is nothing more than the equation of a line. And if you have some line like this here, we know that the point where the line crosses the y-axis has coordinates 0, b. So b is the y-intercept. And we also know that m is equal to the slope of the line. And the slope of the line is just the change in y divided by the change in x. So we also call that the rise over the run. And you can calculate that by subtracting the y values, y2 minus y1, and then dividing that by subtracting the x values, x2 minus x1. So that's just a quick review of lines. So a linear function is just a function that is a line when you graph it. And it can also be written as f of x equals m times x minus x1 plus y1, where m is the slope and x1, y1 is any point on the line. A linear model is an application whose mathematical analysis results in a linear function. All right, let's take a look at some examples. So in the first example, it says at the end of each year, Jocelyn's employer gives her an annual bonus of $1,000 plus $200 for each year she has been employed by the company. Answer the following questions. Find a linear function that relates Jocelyn's bonus to the number of years of her employment. Okay, so let's make sure we define our variables here. So let's let x equal the number of years that Jocelyn has been employed, and f of x will be the amount of the bonus. So we know that f of x, the amount of the bonus, is going to be $1,000 plus $200 for every year that she's been employed. So if she's been employed for X years, that will be 200 multiplied by X. And this can be rewritten as f of x is equal to 200x plus 1,000. So just keep that in mind with what we just talked about on the previous page here. We said that a linear function is f of x equals mx plus b. So you can see that we have the value of m, which is the slope, is 200, and the value for b, which is the y-intercept, is 1,000. For part B, it says use the function that you found to calculate the annual bonus Jocelyn will receive after she has worked for the company for 8 years. So for this one, they're basically asking you to figure out what is f of 8. Well, f of 8 is going to be 200 times 8 plus 1,000. And 200 times 8 is 1,600 plus 1,000, which is 2,600. And this is in dollars. In the next part, it says use the function that you found to calculate how long Jocelyn would have to work at the company for her annual bonus to be $3,200. So what they're asking for in part C is, you know, her bonus is going to be $3,200. The question is, how long will she have to work? So again, we know that f of x is equal to 200x plus 1,000. And in this case, we know that her bonus is $3,200, so that takes the place of f of x. So we get 3,200 is equal to 200 times x plus 1,000. And now we can use that equation to solve for x. So if we subtract 1,000 from both sides, we get 2,200 is equal to 200x. And then if we divide both sides by 200, the 200 cancels out here, and we end up getting x is equal to 11. So this means that Jocelyn will have to work for the company for 11 years for her bonus to be equal to $3,200. And the last part says, interpret the slope and the y-intercept for this problem, both verbally and graphically. So for this, I've brought in a graph of what this function will look like. So here we have the y-intercept, which is 1,000, and the slope is 200. So that means every 1 year that she works, her bonus will increase by $200. So after 1 year, we have a bonus of $1,200, etc. Now, what does this mean? Well, the $1,000 y-intercept here means that she will get a $1,000 bonus when t equals 0. In other words, she will get a $1,000 bonus when she is hired. And then after that, she gets an increase of $200 per year. So the slope of 200 is the amount the bonus increases each year. Our next example is a little more abstract. It says, find the linear function f whose input and output values are given in table 1. And then once we do that, it says to find f of 5. So here you can see they have an input value of x and an output value of f of x. And the first one is x is 1.3 when f of x is 4.5. We can write this in a coordinate form like so. And then the second point is when x is 2.6, f of x is 1.9. Now what we can do is we can use this to find the slope of the line, and we do this by subtracting the y values, 4.5 minus 1.9, divided by subtracting the x values, which is 1.3 take away 2.6. Now if we do the math here, 4.5 take away 1.9 is 2.6, and 1.3 take away 2.6 is negative 1.3. And if you divide here and do the math, you end up getting negative 2. So we know that the slope is negative 2. Now we also know that the equation for this function is f of x is equal to mx plus b, or f of x is equal to m times x minus x1 plus y1. And I'll choose to use the second equation here to find the equation of this line. So we're going to say f of x is equal to the slope m, which is negative 2, multiplied by x minus x1. Now for x1, all I need to do is pick one of these 2 points. I'm going to choose the first point, which was 1.3, 4.5. So this is my x1, and this is my y1. If I do that, I get negative 2 times x minus 1.3 plus y1, which is 4.5. And if we do the math here, we get negative 2x plus 2.6 plus 4.5. And this is negative 2x plus 7.1. So this is the equation of the linear function that satisfies the input and output values you see up above. Now what they ask for is, what is f of 5? Well, to get f of 5, we now only have to plug in x equals 5. So this is negative 2 times 5 plus 7.1, and that is negative 10 plus 7.1, which is negative 2.9. And in our next example, we have a depreciation model. It says that table 3 gives the value of a commercial printer at 2 different times after its purchase. So you can see here in the table, After 2 years, the value of the printer is $10,000, and after 3 years, the value is $9,000. So in part A, it says to identify the input and output variables. Okay, that's relatively straightforward. The input variables is going to be your first variable here. So input is going to be time after purchase. And the output variable will be the other variable here, which is the value of the printer in dollars, and the time was in years. In part B, it says express the value of the printer as a linear function of the number of years after its purchase. So this is pretty much just like the problem that we just did. So for part B, I'm going to take my input and output values here and write them as points. And then I will find the slope of the line here by subtracting the y values and also subtracting the x values. And this gives us 1,000 divided by -1, which is -1,000. So this is our slope. From there, I can use the formula f of x is equal to m times x minus x1 plus y1. And I will plug in our slope, which is -1,000. And then the x1 and y1 that I'm going to choose can be either of these 2 points. I'll choose the second point for this one. So we'll have x minus x1, which is 3, plus y1 is 9,000. And if we multiply this out, we get -1,000 times x plus 3,000 plus 9,000. And if we combine like terms here, we get f of x is -1,000x plus 12,000. And then in part C, it says to use the function that we found to find the original purchase price. Well, the original purchase price takes place when time is 0, right? So when something is brand new, we say time is 0 because no time has passed, okay? So when time is 0, let me rewrite that, time equals 0. X represents our time, so we're going to say x is 0. So f of 0, the value when it's brand new, is -1,000 times 0 plus 12,000. And this is equal to $12,000. So that was the value of the printer when it is brand new. And in part D, it says, assuming the value of the printer is a linear function of the number of years after its purchase, when will the printer's value reach 0? So in part D, they're asking when is f of x going to be equal to 0? So that just means we need to plug in 0 for f of x. And then solve for x. So if I add 1,000 to x to both sides, we get 1,000x is equal to 12,000. And I can solve this by dividing both sides by 1,000. And when we do that, we get x is equal to 12. So in 12 years, the value of the printer will be 0. Next, we talk about direct variation. So a linear model of the form f of x is equal to k times x is what we call direct variation. That is, the ratio of the output value to the input value is a positive constant. Models of this type occur frequently in business and scientific applications. So here's an example. If a car travels at a constant speed of 45 miles per hour, the distance traveled by the car in x hours is simply given by f of x equals 45 times x. So you take the rate, which is 45, multiply it by the time, which is x, and that gives you distance. Now, another quick example is suppose you have a job, and let's suppose that you are paid $20 per hour. Your total pay will equal $20 multiplied by the number of hours. So if I call your total pay f of x, and the number of hours that you work is x, your total pay will be 20 times x, which is 20x. So this is just another quick example of direct variation. So now some specifics. If a model gives rise to a linear function of the form f of x is equal to k times x, or sometimes we will simply write y equals k times x, where k is a positive number, we say the model involves direct variation. Now, another way we can say that is we can say y varies directly as x, or we can say y is directly proportional to x. And the number k is called the variation constant, or the constant of proportionality. All right, let's take a look at some examples. So in this example, we look at the temperature-volume relation. We learn in chemistry the volume of a fixed mass of gas is directly proportional to its temperature. Now what that means is as the temperature rises, the volume also rises. So if the volume of a gas is 450 cubic centimeters at 300 degrees Kelvin, find the following. So first of all, we want to find the variation constant K, and in the equation they're calling it V equals KT. Now we have been talking about f of x equals kx, but in this case, since we're representing volume, we're going to call that V for volume, and x is temperature, we're going to call that T for temperature. So that's where they get the equation V equals KT. Now they do tell us that the volume of the gas is 450 cubic centimeters when the temperature T is 300 degrees Kelvin. If you plug in those two quantities, you can figure out K. So volume is 450, and then we have K times T, which is 300. And if we divide both sides by 300, we get K is equal to 450 divided by 300 is reducible to 3 over 2, or 1.5. So that means that our variation model is volume is equal to 1.5 times the temperature. That's one way to write it. Or we can say volume is equal to 3 over 2 times the temperature. So these are the same. One is in decimal notation and the other one is in fraction notation. Now in part B, it says to find the volume when the temperature is 340 degrees Kelvin. So volume is equal to 1.5 times the temperature. So all I'm doing is I'm taking the temperature value and I'm plugging it into the equation. And 1.5 times 340 is 510. So the answer here is 510 cubic centimeters is the volume when the temperature is 340. And for the last part, it says, find the temperature of the same gas when the volume is 300 cubic centimeters. So for part C, we have volume equals 300. So what we're going to do is take the 300 and plug it in for volume here. So that gives us 300 is equal to 1.5 times T. And then we just simply divide both sides by 1.5. And when you do this, you can solve for T. T is equal to 300 divided by 1.5 is 200. So what that means is the temperature will be 200 degrees Kelvin when the volume is 300 cubic centimeters. Now let's talk about inverse variation. Inverse variation is sort of the opposite of direct variation. So in inverse variation, as one variable increases, the other variable decreases. And I'm going to skip down to the formula for it. The formula for inverse variation is f of x is equal to k divided by x instead of k times x. When we have this kind of relation, we say that y varies inversely as x, or we can say y is inversely proportional to x. K is the variation constant, or the constant of proportionality. Now up above here we have an example of such a instance when this is used. So for example, suppose a bus travels a distance of 200 miles. The time that it takes to reach the destination depends on the speed r. And the distance traveled can be determined by the equation r times t is equal to 200. Or if you solve for t, t equals 200 divided by r. So in other words, the greater the speed, the less time it will take. So let's just take that example up above there. T equals 200 divided by r. And let's just notice that if the rate is 40 miles per hour, the time that it would take would be 200 divided by 40, which would be 5 hours. But if the rate is 50 miles per hour, then the time that it would take would be 200 divided by 50, which would be 4 hours. So you can see that when the speed increases, the time decreases. This is what we mean by inverse variation. Let's take a look at another example. So here we have an example of the price-demand relation. The price of a product is inversely proportional to its demand. That is, P, which is price, is equal to K divided by Q, where Q is the number of products demanded. So if 3,000 units are demanded at $10 per unit, how many units are demanded at $6 per unit? All right. So we know that when the demand Q, that's the quantity, is 3,000, the price P is $10 per unit. So if I have my formula P equals K divided by Q, I can plug those quantities in to get 10 is equal to K divided by 3,000. Multiplying both sides by 3,000 to solve for K gives us K is equal to 30,000. So that means our price-demand equation is P equals 30,000 divided by Q. So the question is, how many units are demanded if the price is $6 per unit? So what they're saying is, if the price P is $6, what does Q equal? So all I need to do is plug in P equals $6, and then I can solve for Q by multiplying both sides by Q, which gives us 6Q is equal to 30,000. See the Q's here cancel out. And then we can solve for Q by dividing both sides by 6. And Q is equal to 30,000 divided by 6, which is 5,000. All right, now this might seem a little bit counterintuitive, but basically the more people want something, the more will be produced. And when there's a higher quantity, the price goes down because it's not as rare. So for the price to go from $10 per unit down to $6 per unit, we need to make 5,000 of these items as opposed to making 3,000. So as the demand goes up, the price goes down. Now, of course, this is an oversimplification of an economic example, but these are just the basics, and this is a good way to talk about inverse variation.